I know that took a while, but I think that was very worthwhile. And we covered a lot of things in here that honestly, this lecture has a lot of concepts which you probably now understand because we just did that exercise. So dimensional modeling is just a design technique, right? And what we're doing is your dimensional model is your fact table and your dimensions, right? So back here, there's one dimensional model. There's the next dimensional model. There's the next one. And you can see, right, if I were to implement this, I would have 1, 2, 3, 4 fact tables, and then, you know, a few dimension tables. And they would get reused mostly. Okay, so how does this work with Inman stuff? So the red boxes, they do not contain dimensional models. You don't put dimensional models in the ODS. You don't have them over here in cross-media storage. You don't have them over here in the external world applications. They only exist in the enterprise data warehouse and the data marts and the DSS applications, right? This is part of data warehouse. What Kimball does is Kimball kind of slices this way, and he has like 2 parts. He has 3 parts. He has this part, this, and then he has a BI. All right, so we kind of talked about all this. I'm not going to spend a lot of time on it. Fact table, dimension table, attributes are columns in your dimension. Star schema is the whole layout. Okay, so here's an example of a star schema, right? Your fact table goes in here, your dimension tables are on the outside, and it's always many to one. Always many to one. So this fact table has a bunch of foreign keys in it, and they just go out to your dimensions. Okay? And again, if you cannot query what you want with this structure, then you need to rewrite your facts so that you can. You need to redesign your fact table so that you can. I've never seen a dimensional model that looked anything different than this. Now there's a couple of derivations of this, okay, and we'll discuss them. But for the most part, they all look like this, right? This is in the middle, high volume, right? You're going to have the most rows in here, and then these rows are very lean and light, right? There's only 365 days in a year. So that's why there's 365 rows over. There's only 25 locations in this company. That's why there's only 25 rows over here. But there's 3 million rows here, which are sales. 1 row written every time something was sold. So attributes are just columns in the key, right? You got the fact table, you get the foreign keys, all common stuff. So let's get into some of the details now. So the rule of fact table design is that your primary key in your fact table is not a surrogate key. You do not want to use a surrogate key. The reason is you can accidentally insert the same fact more than once if you do that. So what you want to do is you want to pick out the minimal amount of foreign keys that you have to guarantee that you're not going to repeat a fact. And by nature, you should never have nulls in these foreign keys. Okay? You want a fact that gets written to always go back to a dimension. If that fact doesn't have a dimensional value, like you write the fact and you don't know the customer yet, which can happen, that's called a late arriving fact. When those kinds of things happen, what we do is we write a code. We have some kind of key, like we might have, you know, customer unknown, and that has a customer ID of -1, right? And then we write that in there so that when we go to look at the dimensional model, we can actually query on, all right, how many orders have the customer unknown right now? Because they were anonymously putting things in their shopping cart, and they haven't signed into Amazon. They're just anonymously adding things to the shopping. So you want to avoid nulls at all costs. Instead, you want to use what are called flags, which are special values that you add to the primary key table or the dimension. Another one is no shopper card. You ever go to Wegmans, not have your shopper card on you, and you buy stuff, and then they just use like the cashier's shopper card, right? The smart grocery stores don't use a personal employee shopper's card. They have one that's flagged as they got a shopper's card discount without using their shopper's club card, right? So that when they go through the analytics of what you purchased, they can find out who's getting discounts and not using their own card, right? As opposed to misrepresenting the discount on some employee's card. So the granularity of your fact table should be at the lowest, most detailed atomic grain captured by the business process, right? And this is what I just showed you. You want to make sure that your facts are at the right level for your dimensions and that you're not including dimensions that aren't appropriate for the fact that you're capturing, right? The facts themselves should be additive, right? And if you have one that isn't additive, you want to redesign it so that it is additive somehow. And make sure that all the facts, if you have more than one fact in your fact table, they're all the same grain. You don't want to add one fact that counts how many people have logged in and then another fact that tells you if a person logged in. That's inappropriate, right? You want that one row has to mean one thing and everything has to be counted the same way across the different things.
Professor, can you give an example where we have to redesign it to be as additive as possible?
Yeah, so a great example of that would be this one, right? So you could design it at this and not do this, right? But the rule of thumb is that I would not use this as my fact table because it's not as granular as it could be. I could go lower, right? I can't go any more detailed than this, right? I can't go any more detailed than that. But I definitely can't go any more detailed than this. But this, I can go more detailed. So the rule of thumb is you should not use this fact table until you recognize there's a good reason to use it. You should use this fact table. Because this fact table can implement what this one does. So that's kind of what I'm saying on that slide. Okay. So let's take a look at, here's a sample fact table that I made for you. And let's see if we can identify what's wrong with my fact table. So this is a fact table that has, here's my primary key for it, here's a player ID, here's a game ID, here's the number of shots that the player took, here's the number of shots that the player made. These are facts, right? And then here's the number of points they scored, there's another fact, right? And then here's their points per shot and their shooting percentage. Those are my fourth and fifth facts. So there's a couple things that are wrong with this fact table based on the slide that I just showed you, right? Based on that slide. So what's one thing that jumps out to you immediately as wrong with this fact table? I do not want to pick this as primary key because now I can add the same row, right? And the constraint, it'll just give me a number 6. I can add the same row again. As a matter of fact, if you look, that happened right here. That's the same fact. Crap, it was written twice. That's why you don't want to do it. So what should the key be? Player ID and game ID. Perfect, right? That way you cannot write the same fact twice. See that? Also, is that a great foreign key? No, right? You should always use surrogate keys in your dimension tables. Because the volume of data that you write to a fact table is crazy. Okay? And believe it or not, using varchar like that is going to slow it down. You want to use all ints and decimals. You can get away with it. Okay? That's going to make it super fast. And you also want your fact tables to be lean, right? You know, one thing you probably didn't care about when you took 659 is how many bytes does each row in my database table take up? Who was that a concern that your professor addressed with you? Probably not. Because storage is cheap. In the data warehousing world, we want our fact table to be as minimal as possible in terms of the number of bytes per row. Because they're going to have so many rows. Okay. So that's another one. Do you see anything else from here? How about these facts? Are these all appropriate to the grain? The grain is Jordan played this game. So this fact 7, is that in context with the player in the game? He took 7 shots in the game. Yeah, works. What about the rest of them?
Points per shot.
Correct, right? These values here are not additive. And they're also redundant. You never want to store a redundant value in your fact table. That's what the calculations are for. Okay? There's no need to do that. The only time you might store a redundant value in your fact table is to save on doing the math, right? But you only do that if it's additive. Like for example, I'll give you an example. Maybe you have a fact table that talks about things you purchased, and you bought 2 water bottles at $5 a piece. So you would write 2 water bottles, and then you'd write $10. All right? that makes sense because the $10 is still at the appropriate grain and the 2 is still at the appropriate grain. But we've lost the ability to add these facts up here, right? Can't add those. Because Jordan, you know, if you add these up, is that the appropriate points per shot now? Not even close. All right, so I think you got them all 3 of them. Good job. So you get it, right? Fact tables, minimum. Only things that you want to quantify, the rest are foreign keys. Your primary key is selected from the number of foreign keys required to make sure it's unique. All right, let's talk about dimension tables. Dimension tables should have column names that are extremely descriptive so that the end user knows what they're looking at. Okay, because the dimensions are the way that they're going to slice and dice through their data. They should have no null values in any of the attributes. So like if you do not know a value in a dimension, you should write some default value, like I don't know what this value is, unknown, something. You should put something in there rather than null and leave it up to the user to guess why it's empty, okay? It should be discretely valued, which means 1 row per business entity. So like if it's a customer, 1 row per customer. You want to have the same customer in there twice. We'll see that there's an exception to that rule, but we'll get to that. You want the data to be as clean and consistent as possible. You do not want dirty, messed up data, you know, weird upper cases and lower cases, things that aren't going to query well. You know, Mr. with a period, then Mr. without a period. You want to clean all that up before you add it to your dimension. Your dimension is your gold standard. You should always have a business key so that you can find the data, but you should not use that as primary key because you don't want that to be a foreign key in your fact table. Your fact table wants to use integers. And then you should always have a surrogate key for primary. All right. So what's wrong with this dimension table? There's 6 things wrong with it.
Null value.
I got a null over here. That's not good. There's 1. Primary key is pretty bad, right? I don't want to use a character value. I want to use a surrogate key. This is probably like the business key. I don't want to use that as the primary key. The other ones are going to be, you're going to have to dig a little deeper to find them.
And your example.
What's that? Yeah, Apple's in there twice, right? So I'm not using the appropriate key value for per business key. What's wrong with the product category?
Spelling mistakes.
I gotta clean it up, right? I got fruit spelled wrong. That's not good. It's not gonna roll up very well. If I count the number of fruits, I get 2 here and 1 there. Whoops. See why that doesn't work? Dimension's gotta be crystal clean, super clean, squeaky. And then here's the tough one. What does this mean? Who knows? You don't know. Maybe it means east. If it means east, write freaking east in here. Don't write E. Don't put things in there that people aren't going to understand. Put things in there that people are going to understand and be able to use. Because your dimensions, again, are the ways that people explore your data model, and they're not going to be able to do that if they don't know what E and S mean. They shouldn't have to go to training to figure that out. All right. So the key in your dimension should always be a surrogate key. And they're going to yield the best performance for your star scheme, giving you the most efficient joins, the smallest indexes on your fact table, and the most rows per storage block. The way a relational database stores that data is it stores them in pages, right? About 8K to 16K per page. And so what will happen is you'll be able to fit in more fact rows per page, and that will give you a better query performance. And you saw how long it took to query some of the stuff that I gave you in external sources, right? That's because it's relational and there's it's highly normalized and there's a million joins going on in there. That's exactly what you want to avoid. In data warehousing, you reshape all that data into a simpler format so that you can get around that stuff. You need to have a natural key in your dimension. If you don't, then it's going to be very hard for you to detect if you're accidentally writing the same thing. Right? The damage of a surrogate key is it's unique always, but now how does the user know that the same row isn't added twice, right? So the rule of thumb here is you want to set some kind of constraint on the business key so that you don't accidentally add the same row again. All right, let's look at some cases in detail. So, a conformed dimension is just a dimension where if it's used across several different business processes, it contains all the columns associated with business process A and business process B in one dimension. And I'll give you an example of that. So what I do not have on here, what I do not have on here yet is student enrollments. Did anybody do student enrollments? Okay, student enrollments back there, over there too? Okay, so you probably had a fact row called ads or drops. Did you do ads, drops?
Yeah,
Ads, student ads.
Class enrollment.
Class enrollment. And that implies add, right? You're adding the course, right? You're in the course. And so you might have fact. Whoops. You'll see where I'm going here in a second. Fact, enrollment. And then that was a transaction, right? One row per add to class section. And then this would be enrollment count, probably, right? Enrollment count. Did you guys do the same thing?
We did drop.
You did drop,
Yeah.
okay. One other thing is you probably want to have a periodic snapshot of this as well, right? Every day, what's the enrollment, right? So before we get into that, here's my point, right? They both share the student dimension. Can we agree that this needs the student dimension? It also has a bunch of other dimensions that are not listed here. That's fine. But it needs the student dimension. What Remote Lab has about the student is probably different than what class enrollment has about the student. But there is one table called dim student. And that one table dim student has a bunch of columns in it. Everything that this dimensional model is going to need and that dimensional model is going to need. It's got to have it all. Are you going to know that at once? No, you're not. You're not going to know that right away. Okay, but you have to remember that this is a process, right? And so you'll collect it, and then it gets bigger and bigger, and eventually you'll have everything you need. And that's what I'm talking about here with conformed dimensions. A conformed dimension is you do not want to make two dim students in your data warehouse. It's not good. Don't do it. If you want to restrict what people see, then use some kind of view. Okay? But you always want to have one main dimension that has all the guts, all the good stuff. So one thing that we like to do with our conformed dimensions is we'll make subsets of those dimensions. And the example I have of this is the computer and pool, right? So we want to have one dimension called computer, and there's a column in there called pool, and it lists the name of the pool. But I might make a view called vPool, which is the pool dimension, which is a simplified version of the product of the computer dimension, right? And that dimension would have like pool ID, and that would be the primary key of the dimension. And then the idea is that for a fact grain of detail, I would use the computer, but at a fact grain higher up, I would use the pool dimension. And that's what this is demonstrating. The better example is the one that you know is this one here, right? So pool is really going to be based on the computer dimension, right? But it's going to be the same data at a higher level, so that when we implement this particular dimensional model, which is the count of computers, regardless of user and specific computer count of logins, that information is going to be in pool, but it's not going to have computer, right? So that's how that works. Is you want to be able to reuse these dimensions, yet at the same time not try really hard to avoid situations where you might have to make a copy of the data. That's fine, right? But it's based on the same data, right? It's based on the same source of data. Like for example, to populate the pool dimension, you would actually source it from the computer dimension, and you would not source it from some other dimension, because you want to make sure and guarantee that it's based on it. That guarantees dimensional conformity. that the dimensions all line up. So date and time dimensions, these are generated programmatically during the ETL process or imported from a spreadsheet or whatever. The time dimension that I made you and the date dimension I made you, I just generated them from a spreadsheet, made SQL out of it, imported it in there for you. So there's an example of time dimension. The exception in the time dimension is you don't use like 1 for the date key. You generate a date key based on year, month, day. Is usually how it's done. And then that way, when you're looking at the fact table, it's still an integer, but it has a little bit of meaning so that you have a clue as to what you're looking at, right? So if I have a fact row and it has time ID 7, I don't know what that means, but if it says time ID 2015-0214, I know what that means. So that's the idea behind the date dimension. I've built the date and time dimensions for you already. They're there. Because honestly, that's a headache you just don't want to have to endure. It's not fun. So there's lots of edge cases in here, like dealing with time zones and stuff like that. And dealing with different types of currencies, I believe. When you have a time zone, what you do is, like, let's suppose we have a call center. And the call center has, somebody called the call center, and that's a fact. Sometimes I'll write that fact 4 times. Like, they called, and then what is the UTC date of that call, right? So this is the call date and time based on wherever they are on the globe. And then I'll also write a version that is in universal time, so that I've normalized time, right? Because the issue is that you have to think of globalization, right? Remote lab is just here in Syracuse right now, but what if it's everywhere? Then we have an issue of when you log in, you log in at 9 a.m. If it's Pacific time, it's not 9 a.m. It's 12 p.m. So you have to normalize those times. So generally, you write that same time twice, one for the local time, and then also one for UTC. And you do that for date and time. So write in local, write in UTC. I want to make sure. So I'm going to stop here. We're going to take a break after this slide. And I want to give you just a few minutes. I know we're getting a little late, but we did that activity took a little longer than usual. But there's something really important that we need to talk about here about slowly changing dimensions, which will kind of end the class for us. But before I do that, I want to talk about degenerate dimensions. So there is an exception to the rule with the fact table, where I told you do not write anything to the fact table other than foreign keys and facts. Sometimes you write business keys to the fact table. And the reason that you do that is because they're important to finding the detail of the fact. Like, for example, imagine you have an order, and you want to pull up the actual invoice for the order as you're browsing through the dimensional model, right? You need to know the order number to retrieve the document that represents the invoice. So you store the order number in the fact table, right? And that we call that, when you do that kind of thing, it's called a degenerate dimension, because it's not a fact. It's actually a dimension, but the purpose of that dimension is to get to another resource, to find the actual order, look up the actual order. So this is very common in what we call operational business intelligence, where someone is looking over a report, and then they're like, I really would like to know what went down with that particular order. And then they can drill right through, and then they end up in another system, and then they see the order. And there's a key, the order number that's used to exchange the value to the other system. That's how I get around. So what usually ends up happening is this degenerate dimension is usually part of your primary key when you think about it. I mean, when you write an order to an order fact table, what better key to use than the order number? Because you know it's going to be unique. So that's where it ends up being a little bit of an exception to the rule. So as you go through this, I will kind of help you with that as you're driving around. You're like, what do I do with this? It's not really a dimension. I'm like, it's probably going to go in your fact table. Probably going to go in your fact table. Another example is with airline tickets and flights. So you might have the flight number, is stored as a degenerate dimension, because that way you can then go back and track the actual flood that way. All right, we're going to pick up here because this is very important stuff, the slowly changing dimensions, and I want you to kind of have a little break and come back. Here's a real head scratcher. You have a situation where you have to deal with the fact that your data changes over time, right? So your data warehouse has time variant data, which means it stores data over a long period of time. So you have to have some way to address the fact that a customer might change their phone number, or they might move to a different address, or you used to sell laptops in the electronics department, but now you're going to sell them in the computer department. So you rebranded your department. So you have to weigh with deal with this. We call this slowly changing dimensions. Okay, the point is that at the time that the fact occurred, right, you want to record the customer lives in Syracuse, New York at the time they bought the product. But then when the customer moves to New York City and then they buy a product, you want that same customer to look differently so that when you report them, it's correct, right? If you don't keep the history over time, you only get the current address of the customer and you lose a lot of information that you once had, right? So this is something that we really have to think about. There's four ways to address this. And I'm going to discuss the pros and cons of each of these four. And what I will do is kind of explain to you what the most common one is and why, and go from there. So the first type of slowly changing dimension is overwriting. This is the overwrite strategy. And the overwrite strategy means that when the customer changes their phone number, you just put the new phone number. And if you do this, you are agreeing to lose history. You're saying, I'm okay with the fact that I just rewrote history. Because now if you historically want to find out who buys things in a certain area code, the 3-digit code at the beginning of the phone number, now that's changed. That person used to be under one category, now they're in a different category. So you have to be careful, right? So when is this appropriate? You only want to use type 1 when you're fixing a mistake. You've got dirty data, it got through, and you want to correct or clean up that dirty data. Type 1 makes sense for that. The old value, if it has no significance, you want to use this strategy. If the old value has significance and historical associations matter, do not use this strategy. Again, this is mainly used for error corrections, name changes, okay, that kind of stuff. I wouldn't even use it for email address changes. The other strategy, and this is probably the most common strategy that we use, is the type 2. And the type 2, the strategy is when something changes, we rewrite another row for that dimension. And from this point on, we use the new row. And the old row is there just to preserve history, and the new row is there so that as new events occur and new facts are written, we're using the right data. Okay. This will preserve history. The natural key is repeated. So where am I doing that? Right there. See, this natural key is up there 3 times. It's my red stapler. This red stapler used to be in the accessories department, and then we moved it to the supplies department, and then now it lives in the office supplies department. So the way we count or categorize that red stapler has changed over time, and I want to preserve that. So here's how it works in a nutshell, so that you just get an idea of why this is really cool. When I want to write a fact, how do I know which one of these to use? I look at this indicator over here. It says current row. That tells me which row, when somebody buys a red stapler, which is going to come in with this particular business key for the fact. It's going to come in with that number, not this number, because this is just a surrogate key. Comes in with that. I know to use this surrogate key to write my fact. Not the other two, because I'm only looking for the current row. in the history of all the orders, you know, between 2010 and 2011, any red staplers purchased would use this key because they were already written. Remember, once you write a fact to a fact table, you don't go back and delete it or change it. You don't do that because it corresponds to an event. So that would be written. That's in there. That's still there. But when you go to find out how many things were bought in the accessories department, that red stapler is counted. Then, when you look today to see what was purchased in the accessories department, those orders show up in office supplies, not accessories. Does that make sense? Because this is a very common strategy. Most of the ETL tooling that we use has code that they've written for you that will process this so that you don't have to deal with this. And it's wonderful. Because imagine trying to write SQL to do this, right? You'd be like, whoa, how do I do this? So the row comes in, and I need to check the dates in the current row indicator before I figure out how to write it. Now there's all sorts of logic written for you in ETL tooling. So this is type 2. It's probably the most common way that we deal with it. And it works the best. Now there's another type called type 3. And in type 3, what you do is you do not add a row, you add a column for the new dimension attribute. And this is used typically when you need to, when you care about both values for a period of time. And I'll give you an example. Let's suppose you're switching accounting systems. If you're ever part of a company that does this, not only will you want to just kill yourself, but one of the things that you will experience is that you will need to keep track of your old account codes and your new account codes for a while. Like the way we used to count the beans over here is now this way. And so you need both of those, and you care about both of those. And so what you want to do is you want to incur some kind of change that you can keep track of. I don't have a picture of it. But what ends up happening is in the dimension, you would write, customer, and then you'd say old account code, and then it would have a value, and then there would be another column, account code, and then it would have the new value. And then when you use your dimensional models, people exploring the dimensional model can pick which count code they want. Do they want to use the old one or the new one? We use this a lot for redistricting. If you're going to redistrict sales territories, this is another way to do it, because you might want to see the impact of the change you made. And the only way to do that is to not only have the old value, but the new value, right? So what you could do is you can have a dimensional model that explores sales, and you can look at sales by territory and say, whoa, we have, like the West Coast is just knocking it out of the park, and there's way too many customers out there. So I'm going to redistrict my sales so that it's a little more even across territories, right? You can do that, and then you can actually have a dimensional model that explores the old territory versus the new territory, so you can see how you're doing, right? So that's an example of type 3. So type 3, you're adding a column to the table. Type 2, you're adding rows to the table. Type 1, you're just rewriting the data. The last one is called a mini dimension, and what we do here is when there's a lot of data that changes in the dimension, we take all the stuff that changes and we actually put it in its own dimension. So I'll give you an example of that. In a customer dimension, things like names and emails, those don't change very often. But in a customer dimension, you might have things like, how old are they? Are you in the 25 to 35 age band? Well, what's your median income? Is it between 50,000 and 75,000? These are all awesome dimensional attributes that you want to have in your customer dimension. But those things, as time marches on, those values change, right? And they change often. And so what we like to do in these types of situations is we will have a customer dimension with the things that don't change very often. And then we'll take make another dimensional table with the things that do change very often. Call it customer demographics dimension. And now our customer will consist of both of these dimensions. And then that way, as people's age bands and income bands change based on annual surveys that we might give our customers, we can address those, but not necessarily write an extraneous amount of rows to the customer. Because if let's suppose you're a customer, right? And we have your date of birth up here. And so, now you're in a different age band. So now we rewrite you, let's suppose this isn't you. We write you again up here, so now there's 2 of you. Then you move. Now there's 3 of you in there. Now we send out our annual survey, and your income has changed. Now there's 4 of you in there. And now you know, got older again. There's 5 of you in there, right? So you can see that if you switch it up this way, there would only be 1 change in here, and then there would be 3 of the changes down here. So you're minimizing the impact of the number of changes that you have in the dimension. Changes are necessary on dimensions, but you want to try to minimize them if at all possible. So it's just another way of thinking about dealing with the fact that you have a lot of changes. And this only really happens when you abandon values or changes of values. And this happens a lot. Like we want to market to certain demographics, right? This is where data mining comes in. You might say, well, what's the significance of this particular gender and salary and age demographic on a particular product that we sell, right? And so you need to have those demographic bands to do it. Those demographic bands are changing often, so you want to have them in a separate dimension because that way they don't affect the underlying customer dimension.
The new dimension, I mean, what kind of changes? Is it type 1, type 2?
It's all type 2, right? These would both be type 2 type of changes. But the idea is that you take the frequent type 2 changes and then put them in their own dimension. You could make them type 1, but then you're going to be rewriting history, and you don't want to do that, right? If someone was 25 years old when they bought a bicycle, and now that they're 35 years old, they're not buying bicycles anymore, they're buying kids' bicycles, right? You don't want to rewrite history and then associate the 35-year-old with the bicycle. Right? You want to keep the history that when they were 25, they bought a bicycle, when they're 35, they bought kids' bicycles. But you deserve it. So I talked about this, role-playing dimensions. All this is you're aliasing a dimension so that it fits within the role that it was designed to accomplish. So we do this a lot with addresses and dates and airport codes and things like that. So for example, a date, you might have order date, ship date, delivery date. They're all the same date dimension. Okay, they're just either you make a view or you make some kind of table synonym so that it represents the different roles that it might play in your dimensional models. The other one is address, right? You want to have a dimension called address, right? Or maybe that dimension is part of customer, but most people like to just have an address dimension. And then address dimension might be the ship to address or the bill to address, right? It might be the address where the supplier is, right? So you have all these different roles that address dimension would play, but now you can just easily disperse geographic information by address regardless of the role that it plays. It's all. So sometimes you have a situation where this is really this is pretty common, where you have all these dimensions, but you make a dimension and there's one column in it. And then you make another dimension, and there's just one column. And so, like for example, how often, for our customers, for our invoices, do we give them net 10 or net 15? How long do we give them to pay us, right? And are the orders by web, fax, or phone, right? And so you might think, well, are these like? I can make something called order mode dimension, and it would only have one column in it. And then I can make something called ship mode dimension, and it would have one column in it. And I can make something called payment terms dimension, and it would have one column. Imagine you're back here, right? You're back over here, and you're up here, and you're like, well, I need order mode, and I need ship terms. Ship terms, 1 to 3 days. Order mode. Right? Okay. These are their own dimensions, but you probably don't want to put them in their own dimension table because then what you end up having is a whole bunch of foreign keys in your fact table. So what makes sense is you make a table with every possible combination of these codes, and you call it a junk dimension. Right? And then, like for example, if that particular invoice, if that order has an invoice that is net 10 on the web, shipped by air, that's this row. Oh, maybe that invoice is net 15 over the phone, shipped by freight. That's some row down here that I don't have. So you take every possible combination of everything in your jump dimension, and you make a row for it. And then now you have all your possibilities covered, right? So if somebody places an order via fax and they want it shipped via air, and that customer has net 10 or whatever, in terms of net 10, that 4 is written to the fact table, rather than having a bunch of degenerate dimensions in the fact table, or rather than having a dimension with one column in it, right? Because there's nothing else associated with this other than this, but we want to classify or categorize it by this. So we make this table. Does that make sense? So the rule of thumb is you don't fill up the jump dimension with junk. You only write rows of the jump dimension when you care about them. So as the fact comes in, you'll know, hey, that order was shipped out via air. They made the order via fax, and we gave them net 10 terms. So then you write that out for the jump dimension. Okay, so sometimes we have to do what's called snowflake our dimensions, where we have a one-to-many relationship between two values that are used in a dimension, and it makes sense to keep it in third normal form because this particular dimension is used as part of another dimensional model. And the example I had was computer and pool, right? So there's one computer is in one pool has many computers, that's one to many, right? But there's one dimensional model that just uses pool, and then there's another dimensional model that uses computer, right? So I might make an outrigger dimension. I might leave a pool table, dim pool, dim computer. I might do that. So the pro is you're back in third normal form, you're saving space. The con is it's harder for users to grasp their head around querying it because now it's not a star, it's a snowflake. There's a fact table, dimensions, and then it goes out from there with more dimensions. It gets dirty quickly. This is only desirable when you have part of a dimension that's used at a higher level for a different fact. That's fact table. That's where it makes sense to do it. You'll know you need to do this. You'll recognize you need to do this when you realize I only need part of the columns in my product dimension for a fact table that I have. When you see that happening, you're like, I got this product dimension, but I don't need product ID and product name. I need category for this particular fact table that I need. I just need category. You'll realize now that you need to outrigger that. So you have two choices. You can either outrigger it and take category out of product and make its own fact table, or you can do this and conform your dimension and make a view called dim category that's based on the product dimension. One or the other. You can pick and choose how you need it, right? Generally, it's going to be based on how much volume of data you have and how big your dimension is. If your dimension is enormous, a couple billion rows, you probably want to outrigger it. Okay, if it's small dimension, maybe 1,000 rows, 10,000 rows, you can just probably make a view on it. It's not for performance. Okay. So how do you deal with hierarchies? So there's two other issues you got to deal with: is hierarchies and multi-value dimensions. So when you have a hierarchy, like you have a fact table and you have the customer, right? And then the customers are usually complicated, especially when you deal with the fact that companies are owned by other companies. You have subsidiaries and things like that. So you want to be able to represent that hierarchy in your order. That you want to be able to report that company A bought the product, and then you also want to be able to report that parent company C, which owns company A, also is responsible for purchasing that product. So at a higher level, you can also associate that same order with another company, right? So that's a parent-child relationship. So you have to do this with a bridge table. Yes. So now it's not one to many anymore. It's foreign key to here and then foreign key to that, right? And then this is a bridge. And this bridge just has your standard parent-child relationship pattern where not only do you have both columns, but you also explain which one's the parent, which one's the child, how far it is from the parent and child. Right? Have you ever implemented a hierarchy model like in 659? Did you have to do that?
Yes.
Did you have to do that? It's exactly the same way that you did it there. So the other thing to think about is what's called a multi-value dimension. In the group that was in my office on Friday, we talked about this. So sometimes you have a situation where the fact table and the dimension table are many to many. They're not one to many. Like in the example that we had was you have your class over here, class section, and then instructor. And this class has one instructor. But have you ever been in a class with like 2 instructors? Yeah, it happens, right? Okay. So now you've got this many to many, right? So the question becomes, how do you count that, correct? How do you go ahead and count, the class? If me and Dave Deshave are teaching this class, you don't want to count the class twice. You want to count the class once, but you want to count me as the teacher once, and you want to count Dave as the teacher once. So there's a couple strategies for that. One way that we deal with it when the resource can be divided is we add a weighting factor. And the easiest way to explain this is you have, let's suppose you go to the doctor's, and you get a bill, right? And the bill says you have strep throat and the flu. Ooh, nasty visit, right? So that's 2 diagnoses for 1 bill, right? I need to divide up the fact, which is the amount of the bill, by the diagnosis. So I add a weighting factor. So this over here would say, diagnosis, let's go with strep throat, that's 50% of the bill. And then diagnosis of the flu, that's the other 50% of the bill. So now I can roll up the bill amount and add up how many bills go to strep throat. I can do that. It's just this one gets split. So there have been heated debates as to how to weigh these things. I mean, you get in a room and some people are like, let's just divide it by the number. And then someone's saying, well, you're saying that that's not more important than my stuff, right? Because ultimately when you're doing money, people get, because this is going to go back to some accounting function, right? So that becomes an issue. But generally you just divide it by the number of values. Where it doesn't work is like if Dave D and I are teaching this class, and you roll that up, it would show Mike as teaching a half of IST 722. That doesn't make any sense, right? But if you were going to say this class is in 2 rooms, it would probably make sense to do that weighting factor because we can't be in 2 rooms at the same time. We're either in this room or the lab, right? So you could say it's a 60-40 split between here and the other room, or it's a 90-10 split or a 50-50 split.
Yeah, the weighing factor is dynamically calculated because for each diagnosis bill, there might be more than, some have 3 diagnoses, some have 4. Mm-hmm. So it will be 33% or 25%. So
yeah. So what happens is there's 2 ways you can do this. The simple way is you take, like if you walk in and you have strep throat, the flu, and type 2 diabetes help you, right? You divide those by each of those 3, so each person gets each billing amount gets a third, right? The other way to do it is in the diagnosis, you can put like a base proportion, right? So let's go back to the flu and strep throat, right? So the doctor might spend more time with you if you have the flu than if you have strep throat. So there might be a 2-to-1 weight ratio on strep throat to the flu. And so then when the weighting factor comes in, it gets calculated as 66% and 33% or something like that, right? So that's usually, if you've gone to the doctor in the US and you get the form, the paper form, heaven forbid your doctor still uses this, it has what kind of visit was it? Was it a short visit or a long visit? They categorize the weight of how much time they spent with you. That generally would determine the cost of the diagnosis and how much of the bill amount should go to that. Some of the systems I've seen, they break out the bill amount into the individual parts of the visit. So they did a throat culture and that's costs $5. You go to the hospital, you get aspirin, that costs $10, right? Whatever. Those things are broken out. What we're talking about is the labor, right? The doctor visits with you and meet the consultation part of it, right? That's the part that needs to be broken out. Okay. the things that they give you, like an IV, those have costs. It's the other part. It's always between 0 and 1. It's a decimal value between 0 and 1, so that you can multiply it by this number and then come up with a true cost. That's the idea. Okay, so let's quickly do this. What on the left are the types of dimensions, and on the right are just some examples. So a customer, like for orders and sales leads, that is a conformed dimension. Right? Okay, so start job. So various classrooms on a college campus. It's a conformed dimension, right? What slowly changing dimension type should you use for number 2? If a classroom, if this is no longer a classroom and it becomes a computer lab, do we overwrite that? Or do we need to know that at one point this was a classroom? We need to know, right? 99% of the time, you want type 2. That's what we want, right? There's only 2 cases when you don't. One, you need to know both values for a period of time for the same dimensional model, right? Not at points in time. And then the other one is when you don't care about history. Those are the only 2 exceptions. Items in a restaurant menu. Okay, that's a dimension, right? That would be a really cool fact table or dimensional model. So that's a conformed dimension, right? Is that, what slowly changing dimension type would we use on that? Still type 2? Type 2? Okay. All right. Parts required to repair an automobile as part of a service record. So I need a tire. I need a thermostat. Conform? No. Is it many to many? Yeah, it's many to many, right? Definitely. Instructors who teach a college class. That's many to many as well. The
4th one, can it also be degenerate?
There's more to the parts than just like the part number.
Like,
So that's why I wouldn't count it as degenerate. A degenerate dimension only has one value in it. And would be, so if I said something like part number on a service record, then that would definitely be a degenerate dimension. But you could even argue then, you probably want to make a parts dimension, because there's things that you care about the part, right? Like where it came from. And
correct. If it traces to a certain inventory at certain location, in that case, it would be a degenerate, right?
Yeah. So one of the reasons why I like this example is to point out that these other dimensions are rare. Okay, they're very rare. Most of the time, you don't have these kinds of things cropping up. All right, so we talked about this before, so I won't get into that, right? So I also discussed this at length at the beginning of class, which is do not write facts of different granularity, right? If it's 1 row per remote lab login event, then you are just storing the fact at that event. You're not storing a count of computers that are in use at the time the login occurs. That's an incorrect use of a fact table. Okay, you want to use another fact table for that. So this is where it's common, like it says, example, measurements are captured for each line or except the shipping chart, which is captured for the entire order. That's an example of a no-no, right? So you have a row, and what that row means is I bought 1 bottle. And then you say, well, the cost of the entire order that was shipped, which includes the bottle and the chair, is $17. That's not correct. You don't want to do that. What you want to do is you want to have another fact table just to deal with shipping, or you want to write it at a higher level so that the shipping amount matches the order amount at the same fact rate. And you might lose product in the process, but it is what it is. In reality, you know how this works, right? If you bought things on Amazon, anyone order 10 things on Amazon and then it gets shipped a little here, a little there, right? So the process of shipping is different than the process of ordering, right? And so you would really have two separate dimensional models for that. You see that, right? You would have different dimensional models. Now, tying them together would be kind of cool, and you can only really do that at a higher level. Like you might have to drop out of the product dimension in order to do that. Because we know how much they charge you for shipping, and they charge you for shipping per order, right? They don't charge you for shipping per item. Right? So you can't. Now, internally, they probably have all sorts of other metrics that they care about, but what they show us is per order. So another interesting when this happens is items are received by the box. Yeah, so this is another great example there. So you buy the item, and there's 12 of them, right? So you need to normalize that down to the fact that it's unit price times the fact that there's 12 of them, right? So that you get a true count of the values, right? So factless fact tables are pretty common in academia, and I would venture to say that just about everything that we've looked at on that spreadsheet is a factless fact table. Usually facts have some kind of monetary value that you can add off for something. Our facts are counting things, right? When did you log in? Count that, right? And so these are called factless fact tables. The fact that the event occurred is the fact, right? Oh, well, the event occurred, that's the fact. I try not to use the word fact. So, factless fact tables are, the hardest ones to get your head around. It's very easy to make dimensional models around financial data and, accounting data and orders and things like that, because everybody understands money and it adds up real easy. Where it's much more challenging is dealing with business processes and events that have no quantifiable data. The events themselves are what you want to quantify. That's a little more challenging. Okay, so a consolidated fact table. We also discussed this. So a consolidated fact table is, hey man, I'm doing this, right? But I think I can take this particular fact table and this particular fact table and combine them. I just don't know if I can do that yet. At some point, when you get down to the table level and you actually start filling in facts, you'll be like, holy crap, I have one table that says sales fact, and I have another table that says forecast fact. And they all have the same dimensions, like the date that the sales occurred, the customer, and the region, and this says date and customer and region. Why can't I just make a sales and forecast fact and just have two additional just have two facts in the one fact table rather than having one in each table? And then one of the nice benefits of this is you can now calculate a variance, right? Because you can say, what's the difference between the forecast and the actual sale? I can store that fact table as well. Yay! Great. So this is very common. What I will tell you about the process is usually you just go ahead and you start hammering out your fact tables and you implement them. And then at some point you run common sense over what you're doing and say, I think I can simplify this. But usually it's very difficult to see the fact that you can simplify them right away. It takes a little bit of energy and unfortunately some sweat equity in working through it before you recognize that you can simplify what you've done, right? But as I designed and as you designed, you should probably just enumerate them all, build them all, and then say, you know what, I think I can simplify this. And usually you won't know you can do that until you start filling it up with data and seeing what it looks like. You know, this looks almost exactly like that. Then you can go from there. Okay. So I'm going to leave you with this, right? Here's the do's and don'ts of this. So do not focus on what you already have, like reports, right? Wherever you work, you're going to have, operational reports and stuff like that. You do not want to take a report-centric approach here, right? You make dimensional models that will suit a variety of needs, not just the needs of what somebody needs or what the needs of what they already have, right? And I think I expressed that in the beginning when we were talking about building these out, and you know, you're like, Mike, why did you add that dimension when I don't think we need it? It's like, well, you don't know if you need it or not, add it now, right? Don't just solve the problem that somebody wants, solve the greater problem that you might have down the road, right? That's what we mean by not taking a report-centric approach. Remember that these models they should not and are not departmentally bound. You shouldn't be solving it, just because a data mart occurs in a department doesn't mean that you should consider your data set to just be bound within that department. Think about the entire organization, right? Think across all the organizational needs, and you'll be able to build better dimensions that serve better purposes. Again, dimensional models, finest level of granularity. While it's tempting to just make this dimensional model because it's all you need, remote lab usage, right? This is a better dimensional model because it has more dimensions, right? And that's where you need to think about it. You want to have as many dimensions as you can in your dimensional model. That's being more efficient in your design, right? And then this might be useful, but I can always reproduce that from the other one. And then last but not least, reuse your dimensions. Reuse them, right? And if you have a dimension and you've already built it and then it's missing some attributes that you need for another dimensional model, then you will repopulate that dimension with those attributes. You'll backfill that dimension with those attributes. And that would be a type 1 change. Okay? Right? Type 1, because that column wasn't there, now you've added a column, then you fill it with data. There's no reason to reinsert 1 million customers because you added some things to your dimension. Does that make sense? Right? Imagine you've got a customer dimension and you have 2 million customers in that dimension, and one column you do not have is zip code for whatever reason. And then some other dimensional model now needs zip code. What you don't do is a type 2 change and then re-add 2 million customers with a zip code. Okay, now you've got 4 million rows in your customer dimension. You want to avoid that. That's why Inman suggests that you get this all fleshed out first, right? Whereas Kimball's like, it's okay to build small things and then grow them back into each other. It's more complicated to do so, but at least you'll have your wins immediately, right? You'll get your wins much more quickly by iterating over your data warehouse rather than trying to architect it all at once, design it all at once, and implement it all at once. You'll spend a lot more time in meetings than that. All right, so do you feel a little better about this? Hopefully you do, right? Hopefully after you read Kimball chapter 5 or 6, whatever it was, and then you've seen this, you're feeling a little better about it. Okay, so next week what we'll be doing is we're going to leap into, all right, we know what a dimension and a fact table looks like. Let's actually implement them in a database, right? And we'll actually, if we have time, we will try together to fill it with data, even though we haven't learned ETL yet, right? We'll try to fill it with some sample data so that we can vet whether or not it's right. Because it's one thing to make a table, right? You look at this table and say, yeah, that probably works. And it's another thing to actually throw some rows in it and say, all right, yeah, it looks good to me, or it doesn't look good, right? I think we all need to actually see rows of data to kind of make sense of if the design is correct. And so that is not ETL. What ETL is a way to automate from your OLTP system into your dimensional models, set it and forget it, get it working and you're done, right? But there's something in between that where we have to initially load our data just to play around with it and see if it works. That's what we'll need.